Hey everybody. Before we start our material for today, I want to draw your attention to the web page. So again, as always, there's a link to the worksheets on this web page, and then on the web page for Friday, there's a list of topics for the exam. I had been saying the exam's over chapter 4, but then I looked back and realized that we covered the L'Hôpital's rule, section 3.7, right before exam 2. And so I said it would not be on exam 2, it would be on exam 3. So here we go. 8 problems, 1 from each section of chapter 4, 1 problem from section 3.7, the L'Hôpital's rule. And same thing as usual. There'll be 8, so 8 problems, 25 points each, that's 200 points. And then the best problem gets put into the best column, so then it gets counted twice, the usual thing. At least one problem will be closely based on a book example. Kingsley has got your quizzes, going to put them here during the hour. He's making sure that they all have written on them that on the quiz, it was our hardest quiz, quiz 7, because it's the hardest material this semester. It makes sense that it's going to be hard. But problem 1 was right out of the book example. And I'm having him write on every one of the quizzes, this is section whatever, 4.4, example 7, forget which one it is. But, and I noticed that some of you solved that example using the technique that's taught, solve that problem using the technique that's taught in the book example, not the one that I taught in class. That's cool. A lot of people prefer the example method that's in the book. I like my method, but it's cool that students read the example, learned that method, decided they wanted to do that. But the main thing is, it's a hard problem. It's hard enough if you've read the example and studied it, but if you come into the quiz cold and you haven't done that problem, a problem like that, it makes the quiz all the more difficult. So again, 8 problems, at least 1, and if possible, I'll put 2 on here that are based very closely on a book example. A little bit confused today. All right, here we go. So we're doing, this is lecture 31. We're discussing section 4.7, antiderivatives, which we started on Monday. So, meeting part 1. Is some more antiderivative rules. So I'm going to make a 2-column table of function and particular antiderivative. Actually, I've already lied. I'm going to make a 3-column table. I'm going to have a 3rd column that says y. All right, first function is cos x. A particular antiderivative is sine x. There's no plus c because I'm doing a particular antiderivative, not the general antiderivative. Now, why is this true? This is because the derivative of sine of x equals cosine of x. So that's why an antiderivative of cosine is sine. If the function is sine, then an antiderivative of that is minus cosine of x. And that's because the derivative of cosine of x is minus sine. So if you have sine, you get how I shifted the minus sign there. Okay, if the function is secant of x, squared, or as books tend to like to write it, secant squared of x. Same thing. Anybody know what a particular antiderivative of that is? A particular antiderivative, yeah, Marcy? Tangent. Yeah, tangent. Tangent of x, because the derivative of tangent of x is secant of x squared. Secant of x squared. And then finally, for the function secant of x tangent of x, anybody know what an antiderivative of that is? Anybody know? Yeah.
The derivative of secant?
So yeah, exactly. So an antiderivative would be secant x. So that's because, as Gwen said, the derivative of secant is secant tangent. So remember what I said on Monday. What I remember from freshman calculus, besides being not much, is that I finally began to get comfortable with my derivative rules and using them when I was doing antiderivatives, because I had to check all of my derivatives, or I made myself check them. Okay, meeting part 2. Particular antiderivatives satisfying an extra condition. So let's just dive into our first example. Find the particular, let little f of x be 7x minus 3x to the fifth. A, find the general antiderivative. Well, let's, really sad because I have a great box of colored chalk in my office. I have to put up with yellow. We only get yellow today. Okay, so in this expression, notice that this is a power function with n equals 1, and this is a power function with n equals 5. So when I build the antiderivative, the general antiderivative, I'm going to build a partial antiderivative, and then I'm going to tack on, I'm going to build a particular antiderivative, and then I'm going to put on my plus c. So I'm going to call this thing capital F. It's my convention of using a capital letter for an antiderivative. And I'm going to use the sum and constant multiple rule. So I'm going to have a 7 times something, and then minus 3 times something. And the something is going to be x, using the power rule, x to the 1 plus 1 over 1 plus 1. And over here, I'm going to have x to the 5 plus 1 over 5 plus 1. I can't stress enough to not skip this step. This is kind of a baby step, but as I've said many times, you string enough baby steps together and it's no longer a baby step, and it's actually quite likely that you'll make a mistake somewhere if you just do everything in your head. So this is 7x squared over 2 minus 3x to the 6th over 6. Oh, and this should say plus c. because it's got to be the general antiderivative. And that needs to go on from the very beginning, not at the very end. And I've got to simplify this some more. This is 7x squared over 2 minus x to the 6th over 2 plus c. Okay, question B. Find the particular antiderivative that satisfies the extra condition that is capital F of 1 equals 5. Well, what I like to do is turn that extra condition around. So 5 equals capital F of 1. And so that's going to be 7. Now, let's just go on. 7 times 1 squared over 2 minus 1 to the 6th over 2 plus c. So this is 49 over 2 minus 1 over 2. So that's 48 over 2. So that's 24 plus c. So how did I do so far? You're scowling. How'd I do? You're shaking your head, so that means you know what's wrong. Generally, when I say, how'd I do, you just yell, you forgot the parentheses, but that's not it. Who can spot my mistake? 1, 2, 3. But isn't 7 times 1 7? Say it again? It's not so much the parentheses, because the only thing inside the parentheses is 1. But what am I supposed to do first? It is an order of operations thing. If you look at that 1, there are two things that are being done to it. It's got an exponent attached to it, and it's got a multiplication by 7 attached to it. Definitely two things are being done there. Which of those happens first? Exponents, order of operations. So this is an order of operations mistake. It's actually a very common mistake for students to make, and it's a bummer because often, it's on a problem where I've tried to make the problem easy by making the x value 1, but then you do something like this and you turn it into a problem where suddenly you're dealing with 49 instead of 7. So actually what this is supposed to be was 7 halves minus 1 half plus c, and so that's going to be 6 halves plus c, so that's going to be 3 plus c. So 5 equals 3 plus c, so that means that c is equal to the number 2. Now, the question, though, was not to find c. The question said find the particular antiderivative. So an antiderivative is a function. So we have to build the particular antiderivative. Capital F of x it's that general antiderivative form, 7x squared over 2 minus x to the 6th over 2 plus 2. So that's an example of a derivative of a function of that form, but it's the particular one where C is the number 2. So this is a particular antiderivative. It's the one that satisfies that extra condition. Before starting our example 2, I want to remind you of something that you're going to be responsible for. Don't forget the unit circle, especially we're getting on to November, so a lot of you who got really helpful unit circle tattoos in various places in September, those are now being covered up by your winter clothing, so you're going to have to just have this stuff memorized. Remember that you need to know really just this first quadrant. So we're going to need to know the important angles. So theta equals 0, pi over 6, pi over 4, pi over 3, pi over 2. Those are the ones in this diagram. Of course, once you have those, you do need to be able to figure out the rest of the unit circle. But you definitely need to know those all the time. And then you need to know the x, y coordinates of the points where those rays intersect the unit circle. And then you also need to know the trig functions involving those angles and those coordinates. So trig function values and inverse trig function values involving those things. So just kind of a public service announcement. Just like, you're going to need to know at some point on every exam, you're going to need to know what e to the 0 is. Most of you get that. At some point on most exams, you need to know what ln of 1 is. Most of you don't get that. You'll say that ln of 1 is 1, or they'll just leave it as ln of 1, and you'll get a point taken off. Just get it. Most of you know that e to the 0 is 1, and the fact that ln of 1 is 0 is the same thing, just turned around. So you're going to, this is famous stuff that you need to know. And again, it's because same thing is over there. Writing quizzes and exams where you don't get to use calculators, we give you numbers that you can work with if you know these things. If you don't know these things, then you've got numbers that you can't work with. So example 2. Find f of t such that f prime of t equals 10 cos t minus secant squared t for t t between negative pi over 2 and pi over 2. And also, f of pi over 3 equals 13. So notice this slight change in language here. Instead of talking about a function little f and its antiderivative capital F, either the general antiderivative or a particular antiderivative, we're now talking about, well, an f prime. We're thinking of f prime as the function, and we're going to be looking for f, which would be an antiderivative of f prime. Well, we're going to take the same approach that we did in this problem. We're going to, although we're not asked to find the general antiderivative, we're going to first do that. So the general antiderivative well, it's going to be called little f of t because it's the general antiderivative of f prime. And by the sum and constant multiple rule, it's going to be 10 times something minus something. Okay, so what goes here? Anybody know? A particular antiderivative of cos. Yeah. Sine t. Okay, you're on a roll. What goes here? Yeah. It should be in your notes from earlier in the hour. You can tap out. Those guys were here. Yeah, good. So notice what I've done so far is I've built a particular antiderivative, but I've got to slap on the plus c to make it the general antiderivative. Now we're going to satisfy the extra condition. So I'm going to turn the extra condition around like I did before. 13 equals f of pi over 3. So that's going to be 10 sine pi over 3 minus tan pi over 3 plus c. All right, well, since I've had my tattoo for so many years that I know what it looks like, I can visualize it. So this I know is radical 3 over 2 sine of pi over 3. And tangent of pi over 3 I know is radical 3 because it's sine of pi over 3 divided by cosine of pi over 3 plus c. So that's five radical 3 minus radical 3 plus c. So that's 4 radical 3 plus c. So I have a one big sentence here. 13 equals this, which equals this, which equals this, which equals this, which equals this. This should say plus c. So we need to find the value of c. So c is going to be 13 minus 4 radical 3. But again, our job was not, we were not sent out to find the value of c. We were sent out to find the particular antiderivative. Here, Gwen. So the particular antiderivative is f of t equals that general form 10 sine t minus, this should be tangent of t here, so minus tan t plus that c. There we go. That's the end of meeting part 2. Meeting part 3 is position, velocity, acceleration. Our book calls this, well, not just our book, it's often called rectilinear motion. Rectilinear means straight line. So remember, for an object moving in one dimension, we use t for the variable, and it's the time, and we have s parentheses t is the position function, and we have v of t, which is the velocity function, and that's s prime. So velocity is the derivative of position. And we have acceleration, which is a of t, and that's going to be v prime of t, which is going to be s double prime of t. All right, so since the velocity is the derivative of the position, we would say that position is an antiderivative of the velocity. And since the acceleration is the derivative of the velocity, we'd say that the velocity is an antiderivative of the position, of the velocity is an antiderivative of the acceleration. And then recall for objects falling under the influence of gravity, well, it's convenient to have the position axis be pointing up and down, pointing up with the 0 at ground level. So use the position axis pointing up with s equals 0 at the ground. So in other words, it looks like this. S equals 0, and then up here, s is positive. If you have a positive position, it means that you're someplace above the ground. If your position is -6, it means, you drove too fast or something. All right. Also, something falling under the influence of gravity has a constant acceleration. So a parentheses t, that is the acceleration function, we can actually just call it the letter a in this case because it's constant, and it's minus 32 feet per second squared. Why minus? Well, because the acceleration is in the downward direction. That's the negative position direction. So that's why the acceleration is a minus 32 feet per second squared. All right, does everybody have one of these? Oh, so if you came in, so if you're sitting by yourself, you need to be sitting by somebody else. So Emily, can you move and sit by somebody? And the people who came in late, can you move over and sit by somebody? Actually, what happened to the person with the green backpack here? Why don't you go over and sit with Emily on that far side? You can go ahead and pause that. Together. First of all, I want to point out that this is a kind of question that would be in the book. A stone is dropped off the tower, 400 feet tall. How long till it hits the ground? How fast is it going when it hits the ground? It's up to you to figure out how to solve that kind of problem. So this worksheet is an example, just one example, showing you the steps you would need to go to get to their answer. If you notice, the back of the page, the last two questions are those two questions. How long till it hits the ground? How fast is it going till when it gets there? So you have to approach this from the information that you know. So for instance, what's the value of the initial position of the stone? Yeah, 400, and that's because, so S parentheses 0, or S of 0 is 400. So if we want to draw a picture of this, we've got this tower sitting on the ground, and it's 400 feet tall. And the stone gets dropped off that tower. All right, somebody else. What's the value of the initial velocity of the stone? Emily was actually doing the gesture. Do that gesture again.
I don't know what gesture I did.
You were doing this kind of thing. Just do that again. This is Emily dropping the stone off the tower. So what's the initial velocity? Emily? 0, because you just dropped it. When would the initial velocity be 5? What would be a situation where the initial velocity was 5? No, not quite. It would be if you threw it, if she was throwing it in the upward direction with a velocity of 5. If she was throwing it in the downward direction with a speed of 5, the velocity would be negative 5. But she just did this, she's dropping the stone. So V of 0 equals 0 because the stone is dropped. Okay, what's the value of the acceleration of the stone? Yeah. A equals constant equals minus 32 feet per second squared. Okay, then, given that the velocity is an antiderivative of the acceleration, find the general form of the velocity function. That is, you want to find the general antiderivative of this thing, but instead of calling it capital A, we're going to call it V. So who can help me out with that? Who knows what's the general antiderivative of this? I want to wait till I get like 5 hands in the air. Silver?
Negative 32 t plus c.
Yeah, wonderful. So V of t is minus 32t plus c. Let's check. If I take the derivative of that, the derivative of negative 32t is just negative 32. The derivative of c is 0, so that makes sense. All right, now, knowing what we know about the initial velocity, what's the particular velocity function that has the correct initial velocity? Got one hand up. want a bunch more. Was your hand kind of up? You're sort of doing this. But which is again, this is a general form of the velocity. What's the particular velocity function that would satisfy that extra condition? It's got to be something of this form, but it's also got to satisfy that up there. You look like you're on the verge of it. Did you get it? Yeah, wonderful. Minus 32t, yeah. So v of t is minus 32t. That's one of these babies. So this is a particular one that satisfies the extra condition that the initial velocity has to be 0. That's the general velocity or the general antiderivative of that. And this is the particular antiderivative, the particular velocity function that has the correct initial velocity. Okay, so there's the velocity function. Now, page 2. Given that the position is an antiderivative of the velocity, what's the general form of the position function? So we have v of t is minus 32t. So what's the general antiderivative of that? I want some new people playing here. Yeah. That would be if you took the derivative. The derivative of minus 32t would be minus 32.
Minus 16t squared.
Exactly. So let's just do that in stages. So s of t would be minus 32, and then I do t to the 1 plus 1 over 1 plus 1. So that'd be minus 32t squared. Oh, and this should be plus c. 32t squared over 2 plus c. So minus 16t squared plus c. That's a general form of the position function. It's an antiderivative. It's the general form of it's the general antiderivative of that. Check it. Take the derivative of this. You get minus 32t plus 0. So that does work. All right. Now, knowing what we know about the initial position, what's the particular position function, the particular one of these babies that satisfies the correct initial position? Got 2 hands up. We're going to use that. So 400 equals s of 0. We know that. So this is from step A. Was that step A? But from step F, we know that s parentheses 0 is minus 16 0 squared plus c. So we use both of those things, step A and step F put together, give us that 400 equals c. But that was not the question. The question was not find c. The question was find the position function. So that means that the position function is actually minus 16t squared plus 400. Now let's check. Does this have the correct initial position? When time is 0, position is 400. Good. Now, does this have the correct derivative? The derivative of this is going to be minus 32t, which is what we needed for the velocity. So that's the particular, again, there's the general position function, the general antiderivative of the velocity. Here's the particular one. So this formula, and actually in our book, there's a problem like this, and they actually do have a question A, which is find the formula for s of t. But you can see, again, that's already, you got to do a bunch of steps to get here. Now the idea is we're going to use this to answer these questions. What's the time when the stone reaches the ground level? How do we find that?
So S of t equals 0.
Yeah. So 0 equals s parentheses t. So that's minus 16t squared plus 400. So 16t squared equals 400. So t squared equals 400 over 16. That's 25. So what's t?
It's 5,
5 or...
-5.
Now that's weird, isn't it? I mean, we're talking about, well, which is the answer for our question?
Positive.
Yeah. What's the speed of the stone when it hit the ground? Yeah, so you do v at time 5. So minus 32 times 5, that's minus 160. Wait, is that it? Really? A negative speed? You can't have a negative speed. You can have a negative velocity, which you should have because the thing's on its way down. But the speed is the absolute value of the velocity. So that's the absolute value of minus 160 equals 160. Now, I want to go back to this. What's up with this? Why do we get that? Yeah, Marcy?
Because this function is a parabola.
Right, but what does it correspond to physically? What's the velocity when the time is minus 5? Marcy?
In real life or in math?
It could be in real life, actually.
0?
No, it's not actually. 160. Velocity is minus 32t. So if t is minus 5, then the velocity would be plus 160. So what's this correspond to? Well, so, it's not like time of the universe began when the stone dropped. There was some stuff that happened beforehand. What could have happened beforehand was, some clown with a rock launcher sat on the ground beneath that tower, and 5 seconds before time 0 fired that rock upwards with a velocity of 160 feet per second. And at time 0, it would have just gotten to the top. It would be still at that instant, and then it would start falling. And so we don't actually know what happened before this stone was dropped. It could have been Emily up there dropping it like this, or it could have been some clown with the stone launcher that 5 seconds previous had launched the thing up. So there's more than one way for the rock to be on the ground in this problem. It could be on the ground 5 seconds after Emily dropped it, or it could be on the ground at time 5 seconds, positive time, after some clown launched it at negative 5 seconds. So it's always interesting to think about the solutions that we reject. They actually correspond to something that could have happened. All right, thank you, Hannah.